We're in Rosen, Discrete Mathematics and its Applications, section 2.4 on sequences and sums. We are continuing our discussion about recurrence relations. In this example, we have a recurrence relation such that the nth term is defined by the two prior terms. So it's equal to a sub n minus 1 minus a sub n minus 2, and this will only be valid when n is 2 or greater, because the recurrence relation can't be applied to a0 since there isn't a to the negative 1 term. It can't be applied to a1 because there's not also because there's not an a to the negative a sub negative 1. So we have to declare those values to be 3 and 5, and those will be our initial conditions. We want to know what are a sub 2 and a sub 3. All right, we'll just calculate those directly. A sub 2 is a sub 1 minus a sub 0. That's our recurrence relation. We use our initial conditions to show that a sub 2 is equal to 2. A sub 3 then will be a sub 2, which we just calculated, minus a sub 1, which is one of the initial conditions, to give us negative 3, 2 minus 5. What about a sub 4? A sub 4 equals a sub 3 minus a sub 2. That's going to be negative 3 minus 2, which is negative 5. Then a sub 5 will be a sub 4 minus a sub 3, which is negative 5 minus negative 3, to give me a negative 2. So one of the things that we can see is that our sequence goes 3, 5, goes up, then it starts to go down, and now it's turned around and started to go up again. All right, a rather famous sequence that is also defined in terms of the two prior is the Fibonacci sequence. And here is the recurrence relation for the Fibonacci sequence. Fibonacci n is equal to Fibonacci n minus 1 plus Fibonacci n minus 2. We can define that for n greater than or equal to 2. We'll need two initial conditions, and for Fibonacci, those initial conditions are f0 is equal to 0 and f1 is equal to 1. All right, let's calculate the Fibonacci series. Well, f2 is equal to f1 plus f0. Initial conditions are 1 and 0, so f2 is equal to 1. f3 is equal to f2 plus f1. That's 1 plus 1. That's 2. f4 is equal to f3 plus f2. That's going to be 2 plus 1. That gives us 3. f5 is equal to f4 plus f3, which is 3 plus 2 to give us 5. And f6 is f5 plus f4. That's 5 plus 3, which gives us 8, and so forth. The Fibonacci sequence is special. We encounter it often in nature. For instance, if you look at the number of patches on a pineapple, they kind of form a spiral in two directions, and the sum of the patches that you take in both directions will be sequential Fibonacci numbers very often. And you can probably think of other places you've seen the Fibonacci sequence. All right, how do we solve recurrence relations given a sequence or given the recurrence relation? It'd be nice if we could have a formula for the nth term rather than having to iterate up to the nth term. And if we could find that, it's called solving the recurrence relation. And when we have that, it's called a closed formula. And we'll only deal with fairly straightforward recurrence relations in this chapter. In chapter 8, we cover them in much greater depth. So the way we will do it in this chapter is using a guessing technique or iterative technique. And then if we needed to, we could use a method called induction to prove it, but we don't cover that until chapter 5. All right, so here we have a recurrence relation, and we have an initial condition. And we want to know if we can find a solution, that is a closed formula for the nth term. Well, one of the way we can do it is by working forward. Just start running that sequence out. So a sub 2 is equal to 2 plus 3, the initial condition, plus the difference. And then a sub 3 is equal to a sub 2 plus 3. But look, if we group the 3's together, we'll get 3 times 2. So this is 3 times 1. And then what about a sub 4? A sub 4 is equal to a sub 3 plus 3, or it's 2 plus 3 times 3. And look at the relationship between the multiplier of 3 and the index. The multiplier of 3 is 1 less than the index in all cases. So a sub n then will be a sub n minus 1 plus 3, but we've determined that the multiplier for 3 is 1 minus the index for a sub n minus 1, and therefore a sub n is equal to 2 plus 3 times n minus 1. So that's working forward. We can work backward as well. A sub n is equal to a sub n minus 1 plus 3, but a sub n is equal to a sub n minus 2 plus 3, and then we have the 3 to get a sub n minus 1, and then we group these to get a multiplier of 2. And here we're tracking the, well, let's see what happens on the next line. And then that is going to be equal to a sub n minus 3 plus 3, but then we'll group these together to get a sub n minus 3 plus 3 times 3. And then finally we're going to get to a sub n minus 2. So we're going to get 3 times n minus 2. A sub 2 is n minus 2. And then a sub 2 is a sub 1 plus 3. Add those together and we're going to get a sub n minus 1. So a sub n is equal to 2 plus 3 times n minus 1. Since a1 was the earliest one, we're able to substitute that right there. And we got the same formula going both directions. All right, that's an example using an arithmetic progression. Let's look at one using a geometric progression. What if we want to deposit $10,000 in a bank account yielding 11% per year? I mean, who wouldn't want to do that, right? The question is, how much would you have after 30 years? And we can set this up as a geometric progression so that this P sub n is going to be the amount of money in year n. Well, it's going to be P sub the amount of money you had in year n minus 1 plus 11% of that amount to give us 1.11 times the year prior amount. We have an initial condition of $10,000. And you can see that this is just a geometric type progression where the common ratio between each year of 1.11. Okay. So let's start from the forward. P sub 1 is equal to 1.11 times P sub 0, but P sub 2 is 1.11 times P sub 1, and then we substitute that in for P sub 1 to get 1.11 squared times P sub 0. P sub 3 then is 1.11 times P sub 2, but P sub 2 was 1.11 squared times P sub 0, so now we have 1.11 cubed times P sub 0, and you can see the relation of the index to the exponent. They are the same, so that we can say that P sub n is going to be 1.11 to the n times P sub 0, and this is our closed form solution for the nth term. And now we can substitute in 30 for the number of years we're going to accumulate money, and we can see that we almost have $230,000. So if you can find a bank account like this quickly put $10,000 into it. And that is recurrence relations.